Okay, I think we're going to get started. If you can't hear me, please come on up. So, welcome to Tampa, welcome to MTT, and welcome to the Aero booth. My name is Grant Wilcox. I am product line manager, or a product line manager for TriQuint, reporting to the Defense Product Solutions Group. So based on that, I'll be talking mostly to the defense markets. However, we are doing a lot of product development and on the commercial side as well. A lot of my talk will be gallium nitride based, and I'll touch on some of the other markets that we're working in gallium nitride, but primarily my talk here today will be on the defense markets and primarily electronic warfare, radar, and communications. So as I mentioned, on the defense side, we are playing in several sub-markets. I'll touch briefly on space. We have a historical portfolio that has supported high-rail space applications for 15, 20 years, mostly on our gallium arsenide product line. I'm not going to really be talking to space today, but if you are interested in space, please get with me afterwards or come to get with your Aero representative, or come to the TriQuint booth and we can talk more about space applications, not only with gallium arsenide, but also with gallium nitride. What I'll be talking to mostly today will be the radar, communications, electronic warfare. A lot of our product development has been across the board for that RF functionality that's going into those markets. Primarily our gallium nitride development has been on the power amplifier side. We're also developing driver amplifiers for those output stages, as well as low noise amplifiers for high robustness. For the other control functions, it's typically gallium arsenide based development. But I'll be talking about, again, the radar, comms, and electronic warfare. So what are the system designers looking for? It's really a swap analysis, size, weight, and power. For your radars, your active electronically scanned arrays, basically everything's higher performance, smaller. You get into your swap analysis, size, weight, and power. So that's really where GaN shines. It allows the system designer to start trading off higher performance for smaller size, lower cost, things of that nature. The radar systems, whether it's airborne, ground-based, or shipborne, we're not making bigger ships, we're not making bigger airplanes, but the end user needs higher performance in those same form factors. So what GaN gives you, a lot of higher power density, so you can get the same amount of power in a much smaller space, less combining, higher efficiencies that results in smaller board sizes or less board space requirements. Higher efficiencies lead to less prime power requirements. So again, it all leads on the positive side of the swap analysis for smaller board space, higher performance, lower BOM costs, things of that nature. So this is I've been using this picture for quite some time. This gives you an idea of the benefits that GaN brings on the amplifier side. GaN really starts to shine as you go higher in frequency. We have very high power performance with our gallium arsenide product line, S-band and below. But as you get higher in frequency, GaN really starts to shine even more so. This is an example of a KU band amplifier. We have 4 6.5 watt gas PAs, which from an equivalent performance standpoint, we can do that same level of performance with one gallium nitride chip. So you can see the board space savings. So if you're combining 4 gas, you can do the same performance or achieve the same performance with one gallium nitride chip. So board space reduction, that reduced combining gives you better efficiencies. Better efficiencies lead to less prime power requirements. So again, very good swap analysis benefit. So this is your basic radar block diagram. A lot of your, not only radar, but a lot of your next generation electronic warfare systems are also going to this type of block diagram. And TriQuint offers the complete suite of RF functionality for these block diagrams. So you can see here's the common leg circuit with the phase shifter, attenuators, things of that nature. Going to your transmit side, right now most of this product development is gallium nitride on the transmit side. Going to this output TR switch. Again, this is gallium nitride switch technology. On the receive side, the LNA, we're doing both gallium arsenide and gallium nitride. The benefit for gallium nitride LNAs is the higher robustness of the LNAs. So potentially for a given system, you can eliminate the need for the limiter if your LNA is robust enough to handle that input signal coming in. So if you can remove the limiter, that reduces your BOM count, reduces your BOM cost, and actually improves your system noise figure by removing the limiter out of the chain. So different form factors. You have your discretes, hybrids, and then your mimics. And a lot of it depends on what you're comfortable with. A lot of it depends on the frequencies that you're working in. A lot of the transistor products is supporting the basically 6 gigahertz and below. We do have some work up at X-band, all the way up through KU band with transistors. The majority of the benefit of transistors comes with the 6 gigahertz and below activity. S-band, C-band radar. There's a multitude of communication applications down in 3 gigahertz and below. The transistor product line shines there not only from a domestic standpoint, but also export friendly. So we can export our transistors. They're all, most of them are EAR99. We can easily export the transistors, allowing the international community access to TriQuint's gallium nitride. So again, and discretes are very easy to work with. They're lower cost, and it gives you the ability to uniquely design for your requirements. Hybrids, a little bit higher frequency. I mean, obviously a lot of C-band communications use hybrid technology. X-band and into the lower KU band also use hybrid technology. This again provides, it takes the matching off chip, puts it into a package. It's a single stage gain product with off chip matching to 50 ohms on both the input and output ports. Again, easy to use, a single stage of gain. Moving up to the Mimic product line, again, it covers all frequencies, anywhere from DC up through W band is what TriQuint has products supporting, but primarily on the radar side, your L, S, C, X, KU, KA band radars all benefit from TriQuint's Mimic technology. So the good news is that whatever form factor that you're comfortable with, TriQuint offers. We offer a growing portfolio of transistors, hybrid amplifiers, as well as mimics. So I'm going to touch on, from a radar standpoint, I'm going to touch on S-band, specifically S-band and X-band radar. As you can see, that this is gallium nitride based products. You can see we're starting with some 2-watt drivers. The feedback from our customers, we have these very high power gallium nitride PAs, upwards of 100 watts, but they want the driver of those PAs to be on the same voltage rail. So they don't want a 9-volt gas driver driving a 25, 30-volt GaN PA. So we've developed we're developing a line of drivers to support our high power amplifiers in gallium nitride. So starting basically with the 2-watt driver, and then a variety of power levels in S-band. So this is targeting S-band radar. You can see good solid 12 and 18 watt. Again, some systems that may be the output stage, other systems that may be the driver stage. But then your medium power levels on up to 100 watts. Now the efficiencies associated with these PAs are in the 50 to 60% range. So highly efficient, high power PAs, allowing for the next generation of S-band radars.
This limit have export license issue?
None of these mimics are ITAR. So most of them are 3A, so they're controlled under the Department of Commerce. So it depends on what country. They may require a license, but it wouldn't be an ITAR controlled license. So that's very good news for the international sales, as these are controlled under the Department of Commerce, so we can generally export them. So all those PAs that I showed on the previous slide will be packaged. Some of them are only available in bare die now, but at the end of the day, the plan is to package all of them. This is an example of the 10-watt PA. It's in a 5x5 air cavity ceramic QFN. So good thermals, small size, very handleable, good performance over the 2.7 to 3.7 gigahertz band, flat performance at roughly actually a little bit higher than 10 watts, 10 to 12 watts, but good thermal management at 50 to 55% efficiency. And this is an example of the 100 watt MMIC. Again, we plan to package this. It's not available in a package today. Later in the year, we'll have this in what we call our CP package. It's basically a pure copper-based package for very good thermal management. But you can see good 100 watt performance over the 3.1 to 3.6 band, and then upper 50s in power added efficiency. And keep in mind that this is our products can generally operate long pulse. So there's a lot of products on the market that are short pulse only, but a lot of our MMIC products and packaged products can operate long pulse.
Do you have pulse performance data?
This is pulse data, yes. But we also have CW data available. Yeah, so this is pulse data. I'm sorry?
The job?
Well, it's a 50 millisecond pulse width with 30% duty cycle. This data. Now we also have CW data on these parts.
It's also can test on CW.
Yes.
How about the output power?
I mean, it'll drop slightly, but not too much. I mean, I don't remember off the top of my head what this particular part will do CW, but we do have CW data associated with this, and I believe we have that on our data sheet. And then you can play around with the bias levels. This has power bias anywhere from 24 volts to 32 volts. So anyway, I mean, so you can play around with the bias conditions to fine-tune what power levels, what performance you need. But a lot of flexibility from the user standpoint with these designs.
So what's the upper operating temperature on these devices?
We rate them up to 85C base plate.
And that corresponds to a channel temperature of what?
We typically target to stay under 225 junction. And our technology at 225 meets the million hours of...
Is that true junction temperature? Or
I'm sorry?
Is that true junction temperature?
Through junction?
True TJT, true junction temperature?
Yeah. Well, based on our thermal models, that's what will come out for. So we generally design to 225C junction or below at 85C backside of the MMIC. That 225 correlates to 1 million hours of lifetime. So this is a table of our transistors that we offer, specifically for the S-band and below. So you can see we have a variety of power levels, anywhere from 8 to 10 watts, all the way. This is a 120 watt part right here. This last part that I'll have another slide on is actually a 200 watt part, but it's two separate 120 watt channels, and I'll show an example of that. But you can see, anywhere from 8 to 10 to 200 watts. Drain efficiencies in the mid 50s to mid 60s. DC, the low end, so basically there's a low pass filter on the input of a lot of these. And so if you have the DC to 6, it's a completely unmatched transistor. It's just a packaged transistor. If you have a 3.5 number, there's a pre-match on that inside that package. So it's not fully to 50 ohms. It's just a pre-match, allowing the system designer to better tune for S-band radar, or L-band radar, or something of that nature.
So what's the difference between GaN 25 and GaN 2HV?
So higher voltage. So this is a 40 volt process. This is a 48 volt process.
Still
quarter micron. So it just allows for a little bit higher breakdown. So it allows us to run it a little bit higher drain bias.
Excuse me. Can you back? How about sorry. How about the frequency band at this efficiency?
The frequency band?
Yes.
Yeah. So these are taken off of basically matched at 3 gigahertz.
Only 1 point.
Yes.
If we use from for example 3.1 to 3.5, maybe the efficiency is lower.
It may be a little lower, but that narrow band, you won't get too much lower. That'd be representative of what you would get.